passing by the moon, its cratered surface illuminated by the distant sun. Moving past the bright, glowing gas giant Jupiter and its distinct rings, leaving the solar system behind as the sun shrinks into a tiny point of light, entering the interstellar medium, surrounded by colorful nebulae and dust clouds. The Milky Way galaxy appears as a massive, swirling spiral of billions of stars. Zooming out further to see the local group, a cluster of neighboring galaxies. Galaxies begin to look like tiny dots, forming a vast cosmic web. This is the observable universe, a sphere spanning 93 billion light-years. At the very edge of this sphere lies the cosmic microwave background. This background radiation is the oldest light in the universe, left over from the Big Bang. But what lies beyond this ultimate wall of ancient light? To understand the edge, we must first understand the speed of light. Light travels at 300,000 kilometers per second, the ultimate speed limit. Because the universe is 13.8 billion years old, light has only traveled so far. The edge is not a physical wall, but a horizon of time. Anything beyond this horizon is completely invisible to our telescopes. The light from those distant regions simply hasn't reached us yet. So, we stand at the center of our own observable bubble, wondering. The observable bubble is limited by the age of the cosmos itself. Every observer in space has their own unique observable bubble. Imagine standing on a ship in the middle of a vast ocean. You can only see as far as the curved horizon allows. But you know the ocean continues far beyond what your eyes can see. The cosmic horizon works exactly the same way. The universe is expanding, and it is doing so at an accelerating rate. Space itself is stretching between the galaxies. Discovered by Edwin Hubble, this expansion changes everything. Because space is expanding, distant galaxies are moving away faster. At a certain distance, galaxies recede faster than the speed of light. This doesn't violate physics. Space itself can expand at any speed. This creates a boundary called the cosmological horizon. Once a galaxy crosses this line, its light can never reach us again. It is forever lost to the unobservable universe. Every second, thousands of stars cross this cosmic boundary. The observable universe is actually shrinking in terms of what we can see. So, if we could travel beyond this horizon, what would we find? The leading scientific theory is surprisingly simple. More of the same. More galaxies, more stars, more planets, stretching infinitely. Our observable bubble is just a tiny fraction of a much larger universe. Just like the ocean beyond the ship's horizon is still ocean. The universe beyond our view is still the universe. To know how far the universe goes, we must measure its shape. Einstein's theory of general relativity states space can be curved. There are three possible shapes for the universe. It could be closed like a sphere, meaning it is finite. In a closed universe, if you travel straight, you return to the start. It could be open like a saddle, curving outwards forever. Or, it could be completely flat, like an infinite sheet of paper. Scientists used satellites to measure the curvature of space. They measured the angles of giant triangles across the cosmos. If the angles add up to exactly 180 degrees, space is flat. The data from the Planck satellite revealed something incredible. The universe is flat, with a margin of error of less than 1%. A flat universe means something mind-boggling. It means the universe does not curve back on itself. It goes on forever, without an end, in all directions. Infinity is hard for the human brain to comprehend. It means there are infinite copies of everything. If you travel far enough, particle combinations must repeat. There could be another you, living the exact same life. But this infinity is only true if the universe is uniform. What if the flatness we measure is just local, like standing on a flat field on a round Earth? To explain why the universe is so flat, scientists proposed inflation. A fraction of a second after the Big Bang, space expanded exponentially. It stretched space faster than the speed of light. This smoothing out process left our visible patch perfectly flat. But inflation might not have stopped everywhere at the same time. This is the theory of eternal inflation. while our pockets stopped inflating and formed stars. Other regions kept expanding, creating other bubble universes. This leads us to the concept of the Level 1 multiverse. These bubbles are separated by vast distances of rapidly expanding space. You could never travel from one bubble to another. The space between them expands faster than any spaceship could move. In these other bubbles, the laws of physics are exactly the same. They have the same gravity, the same atoms, the same light. They just started their Big Bang at slightly different times. But there is also a Level 2 multiverse theory, where different bubbles have completely different laws of physics. Gravity might be stronger, or light might travel slower. Some bubbles might not even allow atoms to form. These universes would be dark, empty, and devoid of life. Our universe happens to have the perfect conditions for life. This is known as the anthropic principle. What is driving this endless expansion of the universe? The answer is dark energy, a mysterious force filling all of space. It makes up about 68% of the universe. Unlike gravity, dark energy pushes things apart instead of pulling. As space expands, more dark energy is created. It does not dilute as the universe gets bigger. This means the expansion will continue forever, faster and faster. In the far future, the edge of the universe will change. Nearby galaxies will merge into one giant galaxy, but all other galaxies outside our cluster will disappear. They will be pushed beyond our cosmic horizon forever. The night sky will become completely dark and empty. Future astronomers will think they are alone in the cosmos. They will have no evidence of other galaxies or the Big Bang. The edge of the observable universe will have closed in on us. Beyond that, the unobservable universe continues to grow. A vast ocean of cold, dark, expanding space. No light, no warmth, just the absolute void. This brings us back to the ultimate question. Is there a true, absolute edge to everything that exists? Not just our bubble, but the entire fabric of space-time. Physics currently doesn't have a definitive answer. We are trapped inside a bubble of our own making. A bubble dictated by the physics of light and time. We may never know what lies billions of light years away. Whether it is an infinite repetition of our own space, or a chaotic sea of different bubble universes. Or perhaps something we cannot even conceive. The edge of the universe is a reminder of our limitations. Our technology can only take us so far. The laws of the cosmos act as a natural barrier. But that doesn't stop us from exploring what we can reach. Every year, our telescopes peer deeper into the dark, finding the first stars that ever ignited after the Big Bang, mapping the cosmic web with higher precision than ever. The edge might be unreachable, but the journey is infinite. We are a way for the cosmos to know itself. And as long as we look up, the universe has no true boundary. As we zoom back in, through the clusters of galaxies, back past the beautiful dust clouds of our nebula, back into our own solar system, past the planets, and back to the fragile blue marble we call home.